that many first games have been built around this subsystem, such as 2020 Infinite Recharge and 2021 Ultimate Goal for FTC and FRC. Um, and more recently this year for the 2023 FGC game, where you can use a shooter to separate the hydrogen and oxygen nodes into their separate containers.
Enter the design process. We have to remember that iteration is key to successful design. We have to factor in three things before making a design. One, how compression can change both speed and cargo path of the cargo. Two, how different materials and wheel sizes react to the cargo. And three, how cargo reacts to each shooter differently. After factoring in all these three things, we are set to make a successful design. Remember, it is just as important to make a successful indexer as it is to have a shooter in the first place. When we say indexer, we mean kind of what funnels in your cargo, typically the middleman between your intake and your shooter. Next is what actually makes up a shooter. We know that our shooter has to be A, reliable to where it won't break down mid-match, B, accurate enough to where it maximizes points, and C, consistent so it scores every single time. Mechanically, our shooter is made up of a hood and flywheels.
Okay, great. So now that we know the design process for a shooter and the components needed to make one, let's talk about a step-by-step process of how to actually design one. So these are past designs from BBQ that have been used in old FRC games like Rapid React. So let's start off with the flywheel. So the flywheel is going to be basically what's going to be powering your shooter, what's going to be shooting your cargo. And what you're going to need is it's essentially a really simple system. You can switch the wheels out for essentially you're probably going to use a heavier type wheel, larger wheels, and you can have a wheel or a set of wheels, and you're going to want to have that on a shaft. And you always want to make sure that it's spaced out in the middle, because if it's too much to the left or too much to the right, that will make your balls skew their path in the air. And next, to power it, what you're going to need is you're going to need 1 to 2 motors, and you're going to need a pulley belt system to power it. So for this gearing, what you want to do is you want to have the larger pulley on the motor, and that makes it so that this gearing makes it so that your flywheel is going to be faster rather than having more torque, because the faster your flywheel is, the better the shots you're going to get, the farther they're going to go. So next is the hood. So this is a non-adjustable hood from the Rapid React game, and these are one of the simplest hoods to make. It's essentially like a backboard for your cargo. So imagine having a backboard for basketball. It helps the ball go in, but it doesn't necessarily shoot it itself. And so these can be made out of anything. This one was 3D printed, but you can use cardboard, metal, anything really. The most important part about your hood is that the cargo can roll up it and that it is completely stable when you're shooting with it. Because it moves around, then your shots are not going to go to the right place. So there are two types of hoods. There's non-adjustable hoods and adjustable hoods. So this is the simpler one to design. This is a non-adjustable one. And then, okay. This is an adjustable hood. So an adjustable hood is a little bit more difficult to design and program, but I'm just going to lead you through how to design it. So basically what you're going to need is a rack and pinion. So as you can see, the rack is going to be attached to the shooter hood itself, and that is going to be moving the shooter hood up and down. And then the pinions are going to be on a shaft that is connected to the shooter structure. And so when the pinions move either like left or right, it's going to move the hood up and down. So to power this, what you're going to need is you're going to need a motor and you're going to need the same pulley belt system. However, for this one, you want to have the gearing so that the smaller pulley is on the motor rather than the larger pulley. This makes it so you have more torque rather than more speed. When you're adjusting your hood, you don't need as much speed to adjust it because you're probably only going to be adjusting it a few inches each time. However, it's good to have more torque because some hoods are really heavy if they're made out of metal like this one. Okay. Next, this is if you want to have a double flywheel. So, as you guys know, there's limited motor slots. So you can't have multiple motors for one flywheel and then multiple motors for another flywheel. So what you can do instead is you can gear them together to move you can gear them together to move at the same time. So what you can do is you can have one gear on your first flywheel and have another shaft adjacent to that with the same size gear. That makes it so that the flywheels move in opposite directions. And then on that same second shaft, what you're going to do is you're going to have a pulley that is attached to your top flywheel. And the reason for this, instead of just doing a pulley directly from one flywheel to the other flywheel, is so that the flywheels move in opposition to each other. If they're moving the same direction, you're not actually going to be able to make your shots. You want them to be moving in opposite directions to either intake cargo or exit cargo. So, next we're gonna compare the differences between these types of shooters so you guys can see which one will be best for like you and your team, depending on the game that you use. So, okay, it works again. Okay, so okay, this is a non-adjustable head shooter. So as I said before, it's one of the easiest to design and build. You really don't need to do much for programming as well. So this makes it easy for first-time teams who've never done a shooter before. And however, it can only shoot a limited amount of heights from a limited amount of places because you can't adjust the hood as much, but it still gives you a little bit of range with what you're working with. Next is the adjustable hood shooter. So this one, it has a very large range of motion. You can shoot from a lot of places on the field at a lot of different heights. However, it's high risk, high reward. So the software and design is going to be a lot more complicated than just a non-adjustable hood. However, you're going to be able to shoot from practically everywhere on the field to practically anywhere you want to go. So let's say you're an experienced team, you've done shooters before, this would probably be the route to go for you. And then
Yeah, so the last shooter we're going to talk about is the double flywheel. The double flywheel shooter is unique in the fact that it can be used on both a non-adjustable and an adjustable hood, which makes it very open for teams to mix and play around with what, I guess, scoring, which way they want to score. This double flywheel is also special in the fact that you can add more speed or velocity to your shots, creating more and more cycles for every time you use cycles. And it allows you to flatten the arc of your shot, allowing you to hit more straight shots when you score. Um, it has a lot of scoring potential, and a lot of teams use it to get higher cycles, but it is harder to do. Again, it is another high risk, high reward thing to build. All right, so we're going to show off a couple of demonstrations real quick. So the first video I'm going to play is our team's 2020 infinite retransfer robot, where we use a single flywheel and a non-adjustable hood. As you can see, it goes in a single arc, allowing you to be very consistent with your shots from a certain distance.
can you hit escape?
Wait, let me do that. All right, and our second robot that we're going to show is the 2021 ultimate goal robot that our team built, which is a double flywheel shooter and uses a non-adjustable hood.
Alright, so now we're gonna move on to the software portion of our shooter. So let's imagine a dual flywheel shooter that hits its target dead center every single time. So you might be asking, what's the secret? The secret is PID control. So PID, which stands for proportional, integral, and derivative, is a smart way to control the system. So for our shooter, this means making the flywheel spin at the right speed for an accurate shot. So let's look into these values a little bit more. The p-value, which stands for proportional, measure the difference between the desired speed and the actual speed. We then use this difference to change the power of the motors. If the difference is big, we make a big change. If the difference is small, we make a small change. So sometimes there might be a little error that keeps adding up over time. The integral value looks to fix that. The integral value looks at the error built up and corrects it. The d value stands for derivative and looks at how fast the error is changing. This helps us slow down and prevent from overshooting. So in Java, we're able to create a loop that will loop through all these PID values, adjusting all these three values for speed. By doing this, we're able to make our shooter accurate even when things change, such as voltage and friction. So if we look at this graph on the right, we see that for each value of PID that we add, the more offset that there is, and the more accurate that we get. So you might be wondering, why does PID matter? PID matters because it adapts. It's like having a sharpshooter that can adjust the speed and can distance on the fly. So with PID, we're able to land an accurate shot every single time. So in a nutshell, PID basically makes our shooter super accurate, and it's like having a robotics marksman that never misses. So let's embrace the power of PID and watch our shooters amaze us with skills and precision.
All right, so imagine this, a shooter that always hits its target every time. That's what every single team wants, but how can we actually do that? We can do that by using a simple projectile motion formula. Using the projectile motion formula, we can get the value of we're looking at the horizontal, vertical distance or values. That's what we're looking for. So um, using the first formula, which is d is equal to v squared times sine times 2 theta over g, we can get the distance. And to get the launch angle, we can get half times inverse sine times g times d over v squared. So what do these variables actually mean? D is obviously for distance, theta is your launch angle, v is velocity, and g is the force of gravity. So what do these formulas actually help us with? So let's say we're using a non-adjustable shooter. We're going to be shooting from a set angle. That's going to be our theta. So now that we have our theta, we have to know where on the map or what exact distance we can shoot from. We can use the distance formula for that. That's what we did for 2020 and our 2021 robots, which had a non-adjustable hood, allowing us to hit consistent shots at the target every single time. For non-adjustable hoods, we would want it to adjust the angle of it the further it gets, right? Because it's gonna be changing the further you get away from it. If you saw in the Robonauts video that he showed, he was using an adjustable hood, and it was changing the further he went using a camera. We can use both of the values for that, taking the distance first by using some sort of camera, and then relaying that through the launch angle calculation to find out what angle to keep our hood at. Through this, we can achieve consistency in all of our shots, increasing our scores per cycle, and overall having a better and more effective shooter. That was our presentation. Thank you for listening.
Question for 25 bucks.
Sir, about what's RPM are y'all apply this? I know it's variable,
Yeah.
but what's kind of the range of description?
So for the FRC robot, we're not using any gearboxes on our Neo 550, or sorry, Neo motor. It's a brushless motor, and it's a
Just lose the mic.
okay.
Yeah, give it. If you go on the Rev website, you can see all the stats for the Neo motor. So that's the RPM that we use, and then we geared it up with one pulley, a 16-tooth pulley, and a 32-tooth pulley.
But for the FTC bot, we used a gear ratio on that. We use a gearbox on that. It's around like I think I was like a 25-to-1 gearbox, making our RPM like 450 something. Because we were shooting up from real close and we didn't want to overshoot, so that's why we were aiming for slower.
Thank you.
You mentioned flat, it seemed like flatter trajectories as a result of the dual thing. Is that because of the spin incurred on the ball, or
So the two spin forces act on the ball, kind of like when you shoot a basketball, right? You have the curve going backward, allowing it to stay in the same position in the air. And you can increase this spin on both, allowing you to do a straight shot and have less curve.
Do you run those a 1-to-1 ratio?
Yeah.
Yeah. That's why the
so when you're
pulleys are all the
using two
same.
flywheels, you're trying to shoot a ball that has no spin?
Depending on how much speed you use it.
You're trying to reduce the arc in the air
Yeah.
so that the ball goes farther distances, because when it, like, as you could see in the 2020 the infinite recharge one, the ball arced a lot and didn't go very far of a distance. But in the FEC one with the double flywheel, it didn't arc as much, so it could go a farther distance.
Doesn't that have to do with the shooting angle? I mean, right here, I'm going to get a lot of arc, and here I'm shooting a rifle.
Well, that helps you shoot higher, but also reduce the spin on it so that it isn't going super
I
high.
don't understand how does spin affect arc in your model?
It's more of like the force acting upon it, right? So
Which
the-
force?
The force from the top, like the top roller force and the bottom roller, right? If we're looking, and if we're looking at the FTC bot, there's two forces that, for like the vertical, or sorry, horizontal opposing forces allowing us to shoot straight, right? If we're vertically opposing force, it's gonna shoot straight up, right? Just because we're with the single and with the single flywheel, we're gonna be shooting at arc most of the time, unless we increase up the speed, and that would make it shoot less accurately because at that point we can't control most of the parameters once a year.
So you adjust the whole angle to decide the distance of the shoot. What about the shooting speed? Is that also adjustable?
Yeah, that's adjustable. So on the 2020 Robonauts, like robot, I spoke to them about it, at the conferences and stuff. And what they have, like it also based on how far away they are. If they're further away, right? Like for the FRC game that year, you could shoot from anywhere on the map, right? Or mostly anywhere on the map. But the further distance they went, they would also increase the angle as well as increase the speed.
It's something that you would do in the code. So since the motor has the capacity to do that, you can change it in the code depending on where you are. In FRC, we use a limelight, and that helps us see like how far away we are from the target. For FPC games, you can use cameras and vision code and things like that to see how far away you are to judge where you need to shoot.
Use before
Okay, does anyone have any other questions?
We have a few questions from online. So from Nate, what are some of the problems you guys had to face when building the shooter or when you had to fix it mid-match?
Okay, so when building it, some of the problems you're gonna get is that it's not going to shoot as far as you wanted it to, or you had problems. This year we tried to make a modified shooter that would shoot cubes for the new FRC game, and what we had is we didn't give the flywheel enough time to spin up to speed before we actually fed the cargo through it, and so it wouldn't shoot as hard. So another notice to put out, if you are trying to make a shooter, you want to make sure that you give your flywheel enough time to spin up so that you can actually shoot it as far as it can go versus just a shorter distance. Yeah.
One more problem that we had while we were building was that one wheel would spin faster than the other if we were using a double. That we fixed through PID, correcting the voltage errors and the speed errors through the code. So after that, both of our wheels spun at the same speed.
Alright. We have another question from online from Bless. What type of motors would be best for the shooter? I think she's a part of the FGC team, so I think in FGC they provide you with a specific rev kit. So if you were basically building a rev FTC robot, what motor would you use for your shooter?
I would definitely use a 16-to-1 what is it called? The Dolby motor.
Yeah. The 16-to-1 motors. Not the Corhex ones, but the
HD.
The HD ones,
yeah.
the HD planetaries. Those are really good. In the pictures you can see like the Neos, those are for FRC, but it has a similar style to the other HD ones for FTC. Depending on how you gear it, like let's say you use a bigger pulley on the motor, that's gonna make it go faster. You can also make it spin faster and spin slower and things like that.
Any other questions?
Any other from on?
So far, we have 4 people entered in a drawing. So that's a 25% chance of winning $25. Anyone else have yours?
Like for the shoot formulas for like shooting distance, how would their speed you spin the ball at, the speed the ball actually travels?
So that was something we did through our vision code. We had a specific program in there that used the speed formula, which I think is like distance over, I don't know, something like that. It's been a while
Over
ago.
time.
But
So we're trying to grow.
but we'd measure how long it took us to get to that point, right? The time and then distance using distance like before your vision thing. So that's how we were able to like change up the speed and change up the angle at the same time.
So is it so shooting for different distances? Did you primarily change angle or speed?
Both. It was both. It was
Why both?
because
now you have two variables, so.
yeah, and I mean they're pretty easy to manipulate. Like if we're shooting at the same speed every time, in different distances, we're not gonna hit, right? Because the further out you are, you have to be, like even though it might hit at the same speed. Let's say we're at the third edge of the map, and the same speed is just not gonna cut it, no matter how high we do it, no matter how high the hard, no matter how great it is. We need to increase the speed somehow, whether gradually. For the FRC bot, we pick a specific case from since we didn't have an adjustable thing. But for the FTC bot, since we were shooting very straight, we could change the speed of it to I don't know. So, default we were shooting straight, and if we slowed it down, we'd be shooting at a very small angles and hard, allowing us to hit it less accurately, but we still get points in. Yeah.
What would you say the biggest change you made to the shooting system from beginning to end?
So if we're talking mechanically, for the FRC spot, we decided to have we decided to have two motors spinning it instead of one because in our design we couldn't fit a way for it to be spun from both sides by one motor. That's just not how the CAD was when we designed it. So we decided to have two motors on opposite sides. For the FTC bot, we decided instead of having two motors spin those two flywheels at the same time, we decided to put the motor on one side and have it chain. So both wheels spun at one time, kind of like the double flywheel thing.
Yeah.
Those were probably our biggest things because A, we would lose weight on that, and two, it was easier to put the TID system into it. Sorry,
Which parameters are the guidance control?
I don't.
What parameter are the PID control?
Oh, so it's gonna control the speed. We also have it. It controls the angle for one sometimes, and then we also have it hooked up to the encoders just for that extra data so that it doesn't offset it too much.
Could you clarify what was the Xenos having you just
So basically for an adjustable hood, as I said before, it's kind of high risk, high reward. So for a non-adjustable hood, you're only going to be able to shoot from like maybe 1, 2, or 3 fixed places on the field. For some games, it's more useful to be able to shoot from multiple different places so that you can just make faster cycles. So that's the pro of having an adjustable hood. You can shoot as long as you have your code right where you can see your goal every time and adjust your shooter, you're going to be able to get that shot in every time, no matter from where on the field you are. So that's the advantage. It gives you shorter cycles. You can cycle from anywhere, and it helps you kind of, if something like goes wrong in the game, your cargo moves, things like that. You don't have to worry too much about, losing time, things like that.
For the adjustable hood, were you guys using like sensors to adjust it, or were you adjusting it?
There was the camera, the limelight camera that we used, that would adjust it based off of again distance, and basically on our at the FRC game there are like little stickers that it can detect and that like basically tell us, oh, we're this far away from this sticker, and we use that as a reference point, and then we change the angle based off of that. It would automatically do it. There was no manual like, oh, press a button, it would change it 5 degrees, 25 degrees.
Because manually, you can't really tell how far it would go because from looking onto the field, you can't really tell. So it's always good to have that. Okay, does anyone have anything else that they want to ask?